Welcome back. So, kind of already told you what we were going to do at the beginning of this video. In the last one, we set up this experiment. We're trying to determine if caffeine increases people's pulse rates. So we're taking 60 volunteers, and we're randomly assigning 20 of them to each of 3 treatments. Either they get Coke, black coffee, or caffeine-free Coke, and based on the pulse rate differences before and after the beverage, we can compare those 3 treatments and see if any of those beverages, and therefore whether caffeine, truly increases people's pulse rates. But let's suppose, and I don't know if this is true, so hopefully I don't get skewered in reality here, but suppose that pulse rates differ for those at least 50 years old versus those under 50. Again, I'm not saying that's actually the case, but that kind of throws a wrench into what we've got here. Our design might not determine whether caffeine increases pulse rates because, let's say, if you're 50 or more years old, your pulse rate goes down. Let's just say that. Okay, I never went to med school, I don't know much about biology, but let's suppose more elderly people tend to have lower pulse rates. So if we've got some people in this age group and some people in this age group, and then we randomly assign them to treatments, it's possible that people's ages could be what's affecting the pulse rates and not the caffeine. So we would like to be able to control for that. That's a serious lurking variable. I didn't hide it this time. That's a variable that we should want to control. But how are we going to control for that? I suppose we could just restrict our volunteer pool to those either under 50 or those 50 or more, but we kind of want to be able to generalize our results to everyone. So we can't really control for that in the way we might be able to control some other lurking variables. But there is a way we can do it. What if we split our volunteer pool into people in this age group and people in this age group? And we could do it evenly, or maybe we have more people in this group because there are more people in that age group in general. Whatever, it doesn't really matter. But what if we essentially did the random assignment of treatments within each of these groups? Then we're essentially isolating this factor, and we can determine whether caffeine increases pulse rates within each group separately. That's how we would do it. That's called blocking. By blocking on age group, that turns our diagram into a little bit of a monster here. So essentially what we're doing is we're tweaking our original design because we feel like our response variable depends on age group. So we're going to be randomizing the treatments separately by age group. And again, that's called blocking. So from the very beginning, instead of just assigning treatments from the get-go, we're separating people into their age groups first. And then essentially within each of these age groups or blocks, we are randomly assigning the treatments and comparing the results. So we're essentially doing this entire design for each block separately. At the very end, we'll compare the results across blocks. Okay. Because it's possible that we see differences here and here. Maybe for those under 50 years old, caffeine doesn't really do much. But if you're elderly, maybe caffeine has a bigger effect. If we don't separate by age group here, and we just do it this way, we would never notice that. And our results might say caffeine's not effective, when in reality, it really is, but only for one of these groups, for instance. Okay. This is the simplest type of blocking, where you only have one blocking variable, in this case age group, and there are only 2 blocks. Now there are some more complicated experiments you could do where you have multiple blocked variables, and there are more than 2 blocks for those variables. And you can imagine if you were to draw a diagram of those experimental designs, it would get kind of crazy. But I think drawing this diagram really helps you see all the different pieces in action. Especially when you're blocking, you're seeing that blocking happen right away. And you clearly understand you're randomly assigning treatments for each block separately. And that way, at the very end, you can compare your results. Within each block, you're doing the same exact thing. Same number of groups, same treatments, still comparing results. Okay, so that's blocking in a nutshell. Okay, so we have 2 different experimental designs that we've covered here. In this first one that we talked about, the treatments were assigned to the experimental units completely at random. We didn't separate them at all, and the treatments were assigned randomly, which is one of the principles of good experimental design. This type of design, where the treatments are assigned to EUs completely at random, that's called a completely randomized design, or CRD. So if you're given a prompt and you're asked to design a completely randomized design experiment, that's what it is. And that's essentially you take your EUs, and this is your first step. Just break them into groups. Each group gets a treatment, compare results. When you introduce blocking into it, it becomes a randomized block design if the EUs are randomly assigned treatments separately within each block, which most of the time, if you're blocking, that's going to be the case. Separate EUs into blocks, randomly assign treatments within each block. You could, I suppose, perform an experiment that you don't assign the treatments randomly, but as we've discussed, that wouldn't be a well-designed experiment. So usually, at least for what you know right now, experiments should be one of these 2 designs. If there's no blocking, it's a CRD. If there is blocking, it's an RBD. So just to repeat, the reason we had to redesign our experiment by separating people by their age groups is because this was a variable that we could not really control for. So some of the lurking variables we talked about in the last video, like time of day, what they were doing right before we started the experiment, those are things that we can actually design the experiment around. We can make sure everyone's there at the same time. We can make sure they're in isolation so they don't affect each other during the experiment. Those are things we can actually dictate. But some things, like how old the volunteers are, we're not going to be able to change that to make the experiment work the way we want. That is when blocking comes into play. So blocking is useful if there's at least one variable inherent to the experimental units, something like age, that should be controlled for because we think it affects pulse rates. But we can't control it as the experimenter. Okay? So the things we can control for, we should try to do that as best we can. For things that we cannot control, that would affect the results of the experiment, that's when you need to block. Okay, we've come to pretty much the end of how to design a good experiment. The rest of this video and the next one will be focused on what type of experiment is best, how to design a good experiment, and what can an experiment tell you. But this is a great time, since we're finished with the design itself, to go through what a well-designed experiment does. It compares 2 or more treatments. So anytime you're looking at, say, a diagram or thinking about how your experiment would run and you're thinking of the diagram in your head, there should be multiple treatments in the experiment. If you're only giving one treatment, there's no way to have results that mean anything. Second, it randomizes the treatments to the experimental units. My experience is that this is something students understand, but when they're talking about how they would design their experiment, this is something that gets lost. Maybe they think it's obvious and they don't have to say that because we only really talk about experiments where we randomize treatments to the EUs, but that is an important piece. If you don't assign the treatments randomly, your results are going to be bad as well. Well, not necessarily, but a statistician will absolutely put you to task for that. Third, a well-designed experiment replicates each treatment to multiple experimental units. Remember we talked about the experiment version where we only had one person getting each drink, and the yoga master was really calm even though they downed a Coke, and you don't want that to happen. By replicating each treatment to multiple experimental units, you are reducing the likelihood of something weird happening. The more you can get, the better. You'll notice, since we didn't increase our volunteers in our block design, we actually only have 10 in each block getting each treatment instead of 20. So there is a little more chance within each block and each treatment having a little more variability, but unless you want to double the number of volunteers, that's just the cost of doing business. A well-designed experiment controls for any lurking or confounding variables where possible. Obvious things, easy things that you could do, just making sure that every experimental unit has as similar of a situation as possible for the experiment is key. And there are some easy things you can do based on the context of the experiment that you can control for. But for some of the things that you may not be able to control, some things don't matter. Like socioeconomic status, if you're in poverty, chances are your pulse rate is higher more often. Are we controlling for that in our experiment? Well, obviously not. We're not giving the people in poverty money. Well, maybe for being in the experiment. Anyway, are we blocking people based on that? Also, no. Right? You're probably not going to be able to block on every single variable that could possibly affect your results. You're only going to want to block on variables that you know will have an impact, and that if you didn't block on that variable, the experiment wouldn't be worth it. So we would only want to take on this randomized block design if we felt that if we did it this way, that our results would be so muddled that it would almost be nonsensical. Blocking is kind of a last resort, but it is a good way of designing an experiment if there are any factors that you can't control for, that you think need to be accounted for. So, let us move to an example from AP Classroom. Okay, so now that you know how an experiment should be designed, let's take a look at an example. This is actually one of the free response questions from 2019's AP exam. So, what I want you to do, grab a piece of paper, or you can write this in your notes, either way. I want you to read through this, and there are parts A, B, and C, and this is all that part C says, so you're not missing anything below the screen. I want you to write up your response to this. This shouldn't take more than about 15 minutes or so. So I know that in addition to the video length, if you do this, that is going to be a little bit of time, but I want to see what you come up with here. Maybe don't do it like full out. Maybe just sketch out what you would say, and we'll talk about it when you come back so you can see where you're right and where you can improve a little bit. Okay, so hopefully you've come up with your responses to these, so let's tackle that. Part A, we identify the treatments, the experimental units, and the response variable for the experiment. So this particular free response question does not ask you to design the experiment yourself, but you've got to know pretty much everything you would need to do that, to answer all these questions. The treatments would appear to be the 4 different concentrations of the fungus mixtures. So you've got 0 milliliters per liter, 1.25, 2.5, and 3.75. Those are your treatments. There's only one factor with those 4 levels. So if there were something else we were doing, then we would possibly have more treatments, but this is a 1-factor experiment, so that's really it. The experimental units from the chief grader's response to the AP test from this year, from the year that this test was given. They said that that was, I think, the most missed part of any free response question on the entire exam. Because people wanted to say the experimental units were the insects. But they're not. An experimental unit is the thing that the treatment is applied to. And the treatment needs to be applied to one experimental unit at a time. There are multiple insects in each container. So the insects aren't the experimental units. It's the containers. Right? Because the entire container is getting one of these treatments. Okay? So that is a distinction you need to make. Just because the insects are a living thing and the containers aren't means nothing. The experimental unit is the unit to which the treatment is applied on an individual basis. The response variable, that is what we are measuring or observing when the treatment is complete, and that's going to be the number of insects that are still alive 1 week after spraying. Okay, so for part A, your treatments are the 4 different concentrations. The experimental units are the containers, and the response variable is the number of insects still alive in each container after 1 week. And in order to get an essentially correct, you need to identify all those correctly. A P is if you get 2 of those 3. So if you had missed the containers being the EUs, but you got the other 2 right, you still get a P for part A. And I if you don't get either one. Okay. Part B, does the experiment have a control group? Remember, a control group is essentially you're still getting a treatment, but the treatment doesn't have any active effect. Does one of the treatments follow that? Yeah, there's a fungus mixture that is 0 milliliters per liter, so it has no fungus in it, I guess. So that would be the control group. So if we scroll down to part B, there are lots of edge case notes here. You can pause the video and look at those if you really want to. I'm not going to waste time looking at those. Part B, yes, there is a control group, and it's because the 0 milliliter per liter concentration contains no fungus. So that's the control group. You get an E for that part if you indicate that there is a control group and justify it by identifying it or explaining there is a treatment which contains no fungus. Okay? Partially correct if you're right, partially correct if you're wrong, that there is no control group because every container is sprayed with some mixture. So they're saying you could make the argument that even though you're spraying it with something that has no fungus in it, you're still applying that treatment. That doesn't make it not a control group, so you're not right, but they're still willing to give you a P for that as long as you justify that answer. Or if you're right and you say there is, but you say that this is not a treatment. It is still a treatment. It just doesn't have that active ingredient in it. Okay, and it's incorrect if you don't get either one of those. Cool. Part C. Describe how the treatments can be randomly assigned to the experimental units so that each treatment has the same number of units. You had to know that was going to be one of the parts, right? So the way that I covered it in the video from last time is you can use a random number generator or a random number table. There is a third method that you're going to see here that you could have used. I'm going to advise you against using that. So we're going to go straight down here to their solution here. And this first one is them using a random number generator. Label each container with a unique integer from 1 to 20. Okay, that's another clue that the experimental units are the containers, because that is what you are numbering, not the individual insects. Then use your generator to choose 15 integers from 1 to 20 without replacement. You could have used all 20. They're kind of cutting a corner at the very end here. The first 5 numbers will get the 0 milliliter per liter treatment. The second 5 numbers get the next treatment. The third 5 numbers get the third treatment, and all the other ones get the fourth. If you just randomized the numbers from 1 to 20 into a unique list, you could do it that way too. The fact that they only choose 15 integers, they're just being silly, right? The alternative solution they provide talks about slips of paper, and you may be lured toward this solution because it's shorter, it uses fewer words, but I'm going to tell you right now, if you use this method and you try and draw random slips of a paper from like a hat or something, it is much easier to get dinged for missing something. There is more that you have to include here, even though it doesn't look like it. It's very easy in this method to forget to say something that will knock you down to a P or even an I. So don't draw slips of paper out of a hat. Okay, use a random number generator. And they actually say you can use slips of paper. Don't do that. Random number generators, you could roll a die that has 20 sides. If you already play D&D, maybe you have one of those and that's what you want to use. It works the same way, I suppose. Or you could use a random number table like we talked about in class as well. You could also use a 4-sided die. That's just weird. Okay, I would definitely recommend using the random number generator for assigning your treatments. Okay. If you have any questions over any of the pieces of this problem or design of experiments in general, if you're in class with me, make sure you ask me those questions. I want to make sure that you've got all that down before you take your unit test and before you take the AP test, really. And especially since, we've started this year off, you weren't able to ask me questions in person. If there's anything that you have that is still like in your head fuzzy, that you don't remember, just a vague concept, let me know. We're going to have plenty of time before fall break to talk about these things. And I want to make sure that you understand them because they will come back. Everything you've learned could possibly come back later. But there will be one more video where we discuss what type of experiment you should do given a certain situation and what it is we can use the results of our experiment to say. Some experiments you can say some things about the results, others you can't. So that'll be our last video for the unit. Make sure you're working on those progress checks. Those will be due before fall break. And I guess that's it for this one. So I guess we'll see you in our last video.